ladies and gentlemen, this class recording has started. So, I've mentioned it to you a couple of times, and I'll mention it to you again. One of the reasons why I've chosen to lay out this class the way that I've chosen to lay it out, and why we do this first, and then this, and then the next thing, is because I want to try and make the ideas flow from one to the next. This section on electricity makes use of definitely the first couple of sections that we've discussed. We've already talked about how electricity is related to subatomic particles and pieces of an atom and stuff like that. Today, we're going to use a lot of the terms that we introduced back in Chapter 2 to explain what we see. So, up on the board, there are 5 terms that we introduced back in Chapter 2, Unit 2, when we dealt with energy. So, I want you to take 1 minute, talk to the person next to you, and see if you can remember with a definition or the description of these 5 things. 1 minute, discuss, go. Let's discuss. So, first, energy, a term that we use a lot to explain a lot of different things, and we will continue to do so. What was our working definition of energy? The ability to do stuff, or the ability to change things, or however we want to state it. Work, how do we describe or define work? The thing that moves energy. We have to move an object for it to happen. Not that it makes energy, it transfers energy or changes the energy of an object. Okay? So remember, energy is conserved, so we don't make it, we just move it from one place to another. Okay? Potential energy. How do we define or describe potential energy? Not stored energy. Energy of position. Based on location, this object has the ability to do stuff. Whereas kinetic energy is
when it's happening.
Motion, right? Energy of motion. Mechanical energy, we said, was potential energy and kinetic energy combined together. We actually talked about 3 things that make up mechanical energy. Do we remember the 3 things?
Yeah. No.
Kinetic, yes. Potential gravitational and potential elastic. So those 3 things together give us mechanical energy. All right, good there? Okay, yesterday. Yesterday, we introduced the idea of field theory. First, who proposes the idea of field theory? Michael Faraday. What is Michael Faraday trying to explain with field theory? Well, electric force, yes, but more generally, action at a distance. The idea that there are certain forces out there that can cause things to move or change without actually contacting other objects. There has to be a way for it to happen. So Faraday proposes this idea of field theory, that the area surrounding an object is changed in a way where it can affect other things. One of the things that we use to try and help us explain or describe the field are field lines. So what do field lines look like on a picture? They're arrows, right? Because they have to describe what would happen to an object in this situation. So, today, we are going to draw on a field that we are much more familiar with than electrical fields to help us describe them. All right? And that field that we're going to talk about is gravitational field. Okay? So, all right. Okay, so, right? Florida's maybe a little oversized there, but you get the idea. Okay? All right, so there's the Earth. There's Canada up here.
I see it now.
All right, so what I would like you to do, okay? What I would like you to do, you do not have to draw, you just have to talk. Talk to the person next to you. What would the gravitational field lines look like around the Earth? Gravitational field lines around the Earth. Discuss with the person next to you. Go.
But the gravity's pulling towards it.
I can see that. I'm glad we're focused.
Yo,
All right. So. All right. So we said the field lines represent what would happen to an object in that situation because of that field. Gravity always does what to objects? It brings them together, right? It brings them down, yes, here, right, Kenny? But more importantly, if we're on the other side of the world, it still brings it towards the middle, right? Gravity is always an attractive force. It brings things together. So the field lines always point towards the middle because that's how things move under the influence of gravity. Good there. Okay. Now, keeping these things in mind, right? The energy concepts, the field concepts, etc., 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 okay? Now, let's take a look at this outline that I gave you today and try and use it to make sense of the electrical things that we see, all right? So, today's outline introduces us to the idea of electric potential energy, voltage, current, and resistance. We won't get to all four of them today, but that's what we're doing. The title, how do we get charges to do what we want them to do, right? Charges have energy, the ability to do stuff. How do we harness that energy and make it work for us? Make it do what we want them to do, okay? So, I have to warn you before we go forward, all right? No, it's going to get awesome, all right? Especially in the terms of the animation you are about to see.
Oh gosh.
Like, I mean, seriously, Frozen has nothing on what you're about to see right here, all right? Just you wait, all right? So, here we go. Consider the following. Stealing from Bill Nye. But Bill Nye stole that from somebody else, so anyway.
Who are you stealing from?
Julius Sumner Miller. Look it up on the internet. He's awesome. All right. So, the green spot represents the Earth, or a portion of the Earth. Okay. The yellow circle represents this ball, not to scale. Okay. All right. Are we ready?
Yeah.
Good. Here we go. Okay. Yeah.
Wait, are you kidding?
No. All right. So, taking this object, right, and lifting it from the ground to here. Okay? Let's talk about energy. What kind of energy specifically, Ted? What kind of potential energy specifically? The gravitational potential energy increases. Maybe, although let's not go there just yet. Okay? Now, question. Will this happen on its own? No. Something has to make it happen, right? We have to do work on this object, okay? But, now taking together the things we talked about. If we talk about the gravitational field in this situation, which way are the arrows pointing? Even though they don't show up in this picture, all of the arrows would point down. So when we do work, we're doing work in which direction? Up, but in relation to the field, going against the field. Okay? So, what happens to the gravitational potential energy? It increases. Did we do work on the ball? Yes. Specifically, we did work against the gravitational field. Okay? Good. So far. All right, ready? Next animation. Whoa. Ready? What? I'll try. Ready? Now I'm laughing, so no.
I'll do it.
All right. No, it's pretty bad. So. Okay. All right. It won't stay there on its own. If we let it go, we know that this happens. Energy. What's happening to energy in that situation? Kinetic is increasing as potential gravitational is decreasing because energy is conserved, right? So if we move with the field, right, potential energy decreases, kinetic energy increases. Okay? Good there. I think that's mostly review, right? We added in the idea of the field and the direction of the field and stuff like that, but that's all review, okay? Okay, are we ready to apply that to the new situation?
Yes.
Hopefully. Okay. All right, here we go. We start with this description because we're way more familiar with gravitational potential energy than we are with electric potential energy. But the ideas and the concepts are exactly the same. First, by virtue of the fact that it is potential energy, that means what? Our description of potential energy is energy of location or position. Electric potential energy is the energy of a particle due to its position within an electric field. Gravitational potential energy is the position within a gravitational field. Okay? But they are similar. One of the ways that they are similar is that electrical potential energy is a form of mechanical energy. So before, when we were dealing with kinetic, gravitational potential, elastic potential, now we can add electric potential to that discussion. We won't do problems like that, but know that it's all connected. When a charged particle is moved within an electric field, work is done and the energy of that particle changes. Just like when we move an object, doesn't necessarily have to be a charged object, but when we move any object in a gravitational field, work is done and the energy of that particle changes. Okay? All right. Good there? Picture. A picture that you have. So, here it is. Okay? Yesterday, we talked about electric field lines. We said field lines are arrows. Electric field lines specifically point where?
To the negative.
To the negatives and away from the positives. Consistent with this picture that we have up on the board? Yes. Okay. All right. This yellow dot here, representing a positive charge. Ready? All right. How did we move this charged particle? How did we move this charged particle? There's a couple different ways that you can describe it. Say again? Well, no. That yellow object is the charged particle. We moved it against the electric field. The other way we could describe it, maybe in a little bit more kind of regular person words, right? We moved that positive where? Closer to other positives. Feeling good. Would this happen on its own? No. So we would have had to do what to it? Work. We would have had to do work on it. But doing work on it resulted in this happening. Meaning, what happens to an object if we do work against a field? What changes? In this case, the electric potential energy, because we moved it against an electric field. Okay? So, electric potential energy is increased. You'll notice on your sheet, right next to this picture, there is a series of questions. Letter D says, how can you increase the electrical potential energy of a positive charge? You can write two things that would be correct. Move positives closer, or move it, because it's positive charge, closer to other positives. The other thing that you could write would be what? Move it against the electric field. That basically is the same thing, yes. It's just a different wording of the same idea, right? In both cases, right, Emily, in both cases, we're talking about moving positives closer to other positives, because the electric field always goes away from positives. Oh yeah, D and E are, yes. D and E are exactly the same thing, so you can cross E out. I'm not exactly sure why I wrote that in the post, but. So for D, right, how can we increase the electrical potential energy of positive charge? You can move it closer to other positives, or you can move it against the electric field. Those are both the same thing. Electric field, because there are different kinds of fields, right? There is a gravitational field and an electric field, and there's actually a magnetic field, and we'll talk about that in the next chapter. So yeah, in this case, we're talking specifically about an electric field, because we're dealing with positives and positives. That's right. All right. But, Julian, like you said, this won't happen on its own, right? And if we let this thing go, what's going to happen? As it goes to the negative, what would we see from an energy standpoint? What will go down? Electric potential energy will go down, but what else would we see? When potential energy goes down, what else do we see in response to that? Kinetic energy goes up. So just like dropping a ball within a gravitational field, potential energy decreases and kinetic energy increases. You don't really have a place to write that down, but you need to understand that idea. Okay? All right, good there. How about this?
Whoa.
Okay. Have we changed the energy at all? No. Okay? It's not any closer to the positives. It's not any farther from the negatives, right? That is no change in the electrical potential energy. How did we move that object? Well, we did, right? But the work in this case is kind of weird because it didn't change the energy, right? But how did we move it in relation to the electric field? Let's use a math term. I heard it. We moved it perpendicular to an electric field. right? Is that any different than me going here to here? Does it have any more or less gravitational potential energy at this spot versus this spot? Nope, right? Because the gravitational field is straight up and down, and I'm moving it perpendicular to that gravitational field. So, right, letter F. How can a positive charge move without changing the electrical potential energy? Perpendicular to the electric field. Okay, good with those ideas so far. So to wrap this up and also answer question G, sorry. Okay, so to wrap this up, when work is done against the electric field, electrical potential energy is increased. There are three ways that that can happen. If we move positives closer to other positives, we're going against the electric field. Okay?
So, he didn't really say
Yep.
that.
We can increase electrical potential energy moving positives closer to positives, but we can also move negatives closer to negatives. We can also move positives farther from negatives. In all of those cases, right, we're taking those objects into a place where they don't want to be. Right? Positives don't want to be by other positives. Negatives don't want to be by other negatives. And positives don't want to be far away from negatives. They want to be close to negatives. All three of those things will increase the electrical potential energy of a charged object. Okay? Good there. No, that doesn't change, right? That gets into this a little bit to the next part, okay? Yes, Shirley?
They don't like that energy because the electric potential energy increases when they have energy.
Yep, pretty much, right? If you're doing work on them, right, you're like, yeah, if you want, yeah, you're making, quote unquote, making them angry. That's fine, yeah. All right, so, next picture. You have it down at the bottom of your page. First, I hope we see the obvious difference. Do we see the obvious difference between the two pictures? So, strong electric field, weak electric field. How are we showing that? More arrows, less arrows. Okay? If we move this yellow charge to the left in both pictures, sorry, no animation in this one. Okay. If we were to move them to the left, would the electrical potential energy increase in both cases? Yes. Would it increase by the same amount?
Yes.
No. As an example, okay, let's say I take this ball, right? I hold it this far off the ground, and I drop it and it accidentally hits my toe. Okay? It will hurt because it has the ability to do damage, the ability to change things, right? Now, let's say I take me and this ball together and we go to the moon, okay? Right? And I hold it this high off the ground, right? And I let it go. And it hits my foot. Will it hurt?
Not as much.
Not as much, right? The gravitational field on the moon is weaker than the gravitational field here on Earth. Here. See this formula right here? If you're watching the recording, you don't see it, but, right? PEG equals MGH. Do we remember this formula?
Yes.
Hopefully, right?
Potential.
This is the formula for the gravitational potential energy. M relates to the object itself. That's the mass of the ball. H represents the height of that object off the ground. What did we say the lowercase g represented?
9.
Here on Earth, it's 9.81. It's the effect of gravity, or the acceleration of gravity, or now we can describe it as the strength of the gravitational field. Those ideas are exactly the same, but now we're not talking about gravitational fields, we're talking about electric fields. In this case, the one on the left is Earth. The one on the right is the moon, right? Stronger field, weaker field. We could have the same object, the same height off the ground, and it would hurt different, not because there's anything different about those objects, but because the gravitational field is different. The same thing is true in an electric field. All right? Strong field, weak field. There would be more electrical potential energy on the left than there is on the right. Good there? That leads us into our next discussion of potential difference or voltage. Those two terms are pretty much interchangeable. Potential difference or voltage tells the ability of an electric field to change the electrical potential energy of a positively charged particle. So the ability of the field to change the energy. Or if we want to talk about it in kind of more general terms, the strength of the field. Or the difference in the electrical potential energy of charged particles at different places in an electric field. Sorry. Do your best. Okay. This is like the lowercase g in the MGH formula, right? Except we're not talking about a gravity, we're talking about an electric field. Okay? All right, good? Sorry, people are still waiting. All right. The SI unit for potential difference is called the volt. All right? It's on the back of it's on the front page of the packet that I gave you today. Okay. Like I said, those are the same, that's all the same packet. Okay. So, a volt, 1 joule over 1 coulomb. All right? I don't expect you necessarily to understand that or know that, but joule is our unit for what? Energy. Coulomb is our unit for charge. So we're talking about energy per charge, or how much energy does each one have. Right? And that's how we measure the voltage. Okay? All right. Good? Do I want to do the next part?
No.
I didn't ask you if you wanted me to do the next part. I said, do I want to do the next part? And I will agree with you guys. We will save that for tomorrow, all right? So, there is some homework on the calendar that we talked about before. It relates to electric potential energy and voltage. There it is. Tomorrow, we'll talk about current and resistance and how it all fits together. Prepare yourselves. There's some more sweet animation tomorrow. All right?
Not better than
Look.